So here's a reminder of the things that we know about the derivative. The derivative is the instantaneous rate of change. Derivative is velocity. Derivative is dy dx. F prime and y prime. Derivative is where we find the mins maxes, where we find increasing, decreasing, slope of the tangent line, and derivative is the limit definition of the derivative. The only thing we know about the integral is that the integral is the antiderivative plus c, or big F of x plus c. We're going to add to that understanding today. Today we're going to talk about Chapter 4, Section 2 and Section 3, sort of a blend. It's on the integral of f of x. Here's our second definition of the integral. The integral is the area under a curve, or the area between the curve and the x-axis. Why is it important to find the area under the curve? Well, because integrating is really important. Remember our relationship that the integral of velocity is the position. And this is technically something that you've been doing for a long time. You really just didn't know it. If something was going 60 miles per hour for 2 hours, it's changed its position by 120 miles. Well, basically what you did there was an integral. You found the area under a curve, under the curve v equals 60, and you found this area right here, which is just the area of the rectangle. You did 60 times 2 to get 120. If we had a vehicle whose velocity was 20t, and I wanted to figure out how far it went in the first 2 hours, again, I would just find the integral, or find the area under this curve, find the area of that rectangle, and I could find how far that car went. Things get much more complicated when I don't have geometric shapes. Alright? If the velocity of something was t cubed, trying to find the area under this curve becomes much more complicated because this curve, the area here, is not able to be found using geometry. Enter a guy named Reimann. Alright? Reimann and Riemann sums are things that occur on almost every calculus exam. Reimann said, well, we can estimate the area under the curve by using rectangles formed by the xy coordinates. Riemann sums are the sum of the area of rectangles formed by the xy coordinates of a curve. Okay, so Reimann was attempting to estimate the area under a non-geometric curve like t squared. I'll give you about a minute to copy down our function, t cubed, its graph, and to draw in the Riemann's sums. Okay, so when we're doing a Riemann sum, there's a couple pieces of important information we need to look for. First, what's the area we're trying to estimate? That's given to us by the integral. We're attempting to estimate the area under the curve from 0 to 2 of the velocity function. The second is how many parts. This is a 4-part Riemann sum, which means I want to subdivide the area from 0 to 2 into 4 equal parts. So that tells me that each part is going to be 1/2 wide, right? This first half is 1/2, this is 1/2, this is 1/2, and this is 1/2. So the width of each rectangle is 1/2. The third piece of information is what type of a Riemann sum. Over the next 2 days, we're going to do right Riemann sums, left Riemann sums, midpoint and trapezoidal will be tomorrow. So this is a right Riemann sum, which means that the height of each rectangle is dictated by the height at the rightmost x value. So I'm trying to find the area under the curve from 0 to 2. I'm using a 4-part Riemann sum, which tells me each one is half wide, and it's a right Riemann sum, which means the rightmost x value in that 1/2 range tells me the height. I get the estimation by just adding up the area of all of these rectangles. So the smallest rectangle is 1/2 times the height at 0.5. To find this point right here, to find the height, I just plug the x value 1/2 into the function and I get 1/8. So the first rectangle is 1/2 times 1/8. I'm going to add to that the area of the second rectangle, which is 1/2 times the height right here, which is 1, plus, now I'm on the, which is 1/2 times the height right here. That point is at 3/2 and 27/8, plus the final rectangle, which is 1/2 times 8. I could add all of those up, and I get 100/16. That is my estimation for the area under that curve. So Reimann looked at that and said, well, that's kind of a problem. Obviously, just looking at the picture, look at all this extra area I have. This is an overestimation of the area under the curve. So we try to fix that problem. So instead of doing an overestimation, Reimann said, what if I do a complete underestimation? He said, well, let's do a left Reimann sum in 4 parts. So 4 parts means that each one is 1/2 wide again. So 1/2, 1/2, 1/2, and 1/2. But this time I'm going to let the leftmost point dictate the height. So now I've got 1/2 times the height right here, which is 0, plus 1/2 times the height right here, which we already found is 1/8, plus 1/2 times 1 and 1/2 times 27/8. That estimation came out to be 36/16. But again, he had the problem. This wasn't an overestimation, this is an underestimation, because look at all the area under the curve that I'm completely not counting by doing a left Riemann sum. So same sort of problem. We don't have an accurate enough representation. Well, Reimann came up with a solution to this. His solution was use more rectangles. If I do an 8-part Riemann sum, which don't freak out, we're not going to do because there's a lot of numbers that would be involved. And on the test, they usually tap out at like 5-part Riemann sums. But I could do an 8-part Riemann sum and look at the overestimation. The overestimation in my 8-part Riemann sum got a lot smaller. So he said that's probably the right way to go. So he said, what if we make him even smaller? So you can see that as I increase the number of rectangles in my right Riemann sum, that the overestimation, the amount that those rectangles are hanging over the curve, is going to get smaller and smaller and smaller. So why is this calculus? This is calculus because if we take the width of each rectangle, and we started with 1/2, and then we went to 1/8, and then we went to 0.05, and I keep making that width smaller and smaller and smaller, eventually I just have a whole bunch of really, really infinitely small rectangles side by side by side by side. And if I take these infinitely small rectangles and add them all up, I will have the perfect area under the curve. And that's what Riemann did to find the exact area under the curve. And this sounds a lot like a limit. This almost sounds like when we took the secant line and we took the 2 points and got them closer and closer and they became the same point when we found the derivative. It's essentially the same limiting process, but now we're doing it using area instead of using a secant line. Alright, I want you to practice. Let's do a 4-part right Riemann sum to estimate the area under this parabola from -3 to 5. I'll give you a couple minutes to do that. And every time you do a Riemann sum, at least in the beginning, I would highly, highly recommend that you draw in the rectangles. Alright, so draw the curve that I have here and draw in rectangles that divide -3 to 5 into 4 parts and have heights dictated by the right most x value. Just in case you were struggling, I went ahead and drew in the 4 rectangles we were talking about. I'll give you another 2 minutes to compute the estimation of the area. So I found the total area to be equal to 56. That can be found by multiplying the width of each rectangle, which the width is 2 because that's how I split 8 up into 4 parts by each height, which is dictated by the right point. So this height right here is 17, this height is 5, this height is 1, and this height is 5 as well. Same function now, but this time I want an 8-part left Riemann sum. So with an 8-part Riemann sum from -3 to 5, each rectangle will have a width of 1. Now, on this problem, the left point is going to dictate the height of each rectangle. I'll give you a few minutes to estimate the area under the curve using an 8-part left Riemann sum. Okay, so up on the board you can see my rectangles drawn in, and I have the area of each rectangle listed out. The width of every rectangle is 1, and I'm multiplying by the height determined by the left endpoint. So working left to right, the heights are 17, 10, 5, 2, 1, 2, 5, and 10. I add all of those up to get 52. And I know the Riemann sums between drawing the function and drawing the rectangles and doing all the math is relatively time consuming, but this is usually in an FRQ, so you'll have plenty of time to go through this. And remember, we're only looking to get 3 to 5 points on an FRQ to be able to get a 3 or a 4, so we want to take our time and not mess up any of the algebra or the addition when doing the Riemann sum. Here's your homework for tonight. Again, the answers to these questions and my work will be shown on Edmodo, and if you have any questions, feel free to use Edmodo as a means of communicating those questions to me. Have a good day.